Okay, so now we're going to take a look at examples 2 and 3, which are two different ways of solving the same problem. The problem is we want a formula for the sum of numbers up to some number. So, our function is going to be s of n. And, we can write out a few just to see what it looks like. So s of 1 from 1 to 1 is just 1, so the answer is 1. S of 2, 2 plus 1 is 3. S of 3, 1 plus 2 plus 3 is 6. And S of 6 is 21. So those are pretty straightforward examples, but we want a general formula. We don't want to have to figure it out each time. We want to have a formula we can just plug the numbers into and boom, we get an answer. Well, luckily, we have that formula, and that is n times n plus 1 over 2. So let's plug that in over here. Let's just pick 5 to test it out. 5 times 5 minus 1 over 2 plus 1. 5 times 6 is 30. 30 divided by 2 is 15. That checks out. So at least, and you can try them for all of these, for 1 to 6, it works. Does it work in the general case? Let's prove that it does. So in this case, our n sub 0 is 1, right? So our base case is s of n sub 0, and the answer to that is also 1, which makes sense. Our inductive hypothesis, a sub k, or assertion for k, is that k times k plus 1 divided by 2 is true as long as k is greater than or equal to 1 and less than n. And then our inductive step is to prove that based upon that, our assertion is true for n. Well, s of n is going to be 1 plus 2 plus 3 all the way up to n, right? That's what the sum means. If we add some parentheses, we know it's going to be 1 plus 2 plus 3 all the way up to n minus 1, and then we add n to that series. Agreed? That makes sense. That's the definition of sum right there. Well, what's the sum of that? Since that is the sum up to n minus 1, that is s of n minus 1 plus n. Now, we know that s of n minus 1 is true based upon our, I'm supposed to be underlining there, based upon our inductive hypothesis. This must be true, right? So we know it's true. If we do the algebra, we get n minus 1 times n minus 1 plus 1 divided by 2 plus n. Okay, so now we need to do a little bit of algebra. This is going to become n minus 1 times minus 1 plus 1. Those cancel each other out. We're going to get n, and that's still over 2 plus. We need to get a common denominator so we can add these two together. We're going to get 2n over 2. We can multiply that in. We will get n squared minus n plus 2n. We're going to add this in now over 2. We can pull out the n now, and we'll get n times n minus 1 plus 2 over 2 plus 1, or excuse me, minus 1 plus 2 ends up being n times n plus 1 over 2. That proves our inductive step, right? So going back, remember we have that assumption. We assumed that this was true, right? We assumed it was true for the n minus 1. That's our inductive hypothesis. But once we assume that's true, we need to prove it. If that's true, then it's true for n, which is what we did here. And because of the nature of induction, I could then prove it all the way down to my base case if I had to. Okay? Now, in example 3, they try to lay out an intuitive argument for why this is true. I think it's obvious why it's true. You know, the sum of n is the sum of n plus 1 plus n, right? They try to lay it out with kind of one of those geographic patterns, which works a lot with recursion. The pattern they pick, I don't understand it. There's something missing from their explanation. And they don't actually prove it with induction. So that is not necessary for this chapter. So take a look at example 3. If you figure it out, please explain it to me. But you do not need to understand that for this unit. Okay? Now, if you have any questions about example 2 or the proof for example 2, ask in the forum below.